Okay, in this video we're doing Calc BC Problem Set number 39. Problems in a playlist are in the description below. Let's take a look. Number 1, the functions f and g are differentiable and have tangent lines y equals 5 minus 4x and y equals 3 plus 5x, respectively, at x equals negative 1. Use this information to evaluate the limit above with outstanding work. Okay, so first thing I'm going to do is we have the tangent lines, which means we know the value of the function at negative 1, and we know the value of the derivative at negative 1. I'm just going to write down the values of the function because we actually have to find those. So f of negative 1, for example, would be 5 minus 4 times negative 1, which is going to be 9. And then for g of negative 1, same thing, but the other one. So 3 plus 5 times negative 1, negative 2. All right, so we have these values. Now let's start doing the problem. So this is almost certainly going to be L'Hopital's rule. I mean, you should try to just plug in, you'll get 0 over 0. We have to establish something. So I'm going to say f and g are differentiable, therefore, or that implies f and g are continuous. All right, because they're continuous, the limit equals the value of the function. That's like the definition of continuity at a point. So we can say the limit as x approaches negative 1 of f of x is f of negative 1, which is 9, and the limit as x approaches negative 1 of g of x is g of negative 1, which is negative 2. That's good because if you look at the numerator and you do f of negative 1 is 9 minus 9, you get 0. And then in the denominator, you get negative 1 times g of negative 1. So negative 1 times negative 2 is positive 2 minus 2, 0. So we are getting 0 over 0. So I'm going to write that down. So you want to write it this way. You don't want to write equals 0 over 0. You're not going to get points for that. So we have this. All right. Now what we're going to do is we're going to say the original limit, which we were given, is equal to, let's use L'Hopital's rule. So it's going to be the limit as x approaches negative 1. The derivative of the top is just f prime of x. The derivative of the bottom requires the product rule because we have x times g of x. So it's going to be first, which is x, derivative of the second, g prime, plus second, which is g of x times derivative of the first, which is 1. The derivative of negative 2 is 0, so that's just gone. Now we're going to try to evaluate this. So f prime we can get from the tangent line. So up here we know that f prime of anything, or well, no, f prime of negative 1, not of anything. This is only the tangent there. Sorry, got confused for a second. So f prime of negative 1 is definitely negative 4. In the denominator, we have x is negative 1. G prime of negative 1 is going to be the slope of the tangent, so it's 5. And then plus g of negative 1, which we figured out was negative 2. So we have negative 4 divided by negative 7. So we have, it should be 4 over negative 4 over negative 7. That should be positive. Hold on, I got this. There we go, 4 over 7. And I'm going to say we use L'Hopital's rule, so by L'Hopital's rule. There you go. That's the first problem. Let's take a look at the next one. Given that f of 2 is 3, f prime of 2 is 1/2, f double prime of 2 is negative 1. We want to find the second degree Taylor polynomial to e to the f of 2x at x equals 1. First thing I'm going to do is I'm just going to say that g of x is that thing so I can talk about g of x. So let g of x be e to the f of 2x. I need g of 1, g prime of 1, g double prime of 1. Those are the things we need, and then we'll just punch them into the formula. So g of 1, pretty easy to find. It's going to be e to the f of 2. F of 2 is 3, so that's e cubed. Good. G prime we can find by using the chain rule. So g prime, it's going to be e to the f of 2x times f prime of 2x times 2. And so then we need to plug in. So we're going to get that g prime of 1 is going to be e to the f of 2, f prime of 2 times 2. You can see f prime of 2 is 1/2. So we get e to the third times 1/2 times 2, which is just e to the third again. So then you're like, maybe it's always e to the third. We're not that lucky. We got to find g double prime. So g double prime, we need to use the product rule. So it's going to be first e to the f of 2x times the derivative of the second. So the derivative of the second, I'm treating the second as 2f prime of 2x. So it's going to be 2f double prime of 2x times 2, so 4f double prime of 2x. Plus second, which again we're treating as 2f prime of 2x, times the derivative of the first, which we already found because it's just e to the f of 2x again. So that's 2e to the f of 2x times f prime of 2x. Now we just have to evaluate this. So g double prime of 1 will be e cubed for f double prime of 2 is -1, 2 f prime of 2 is 1/2, and whatever else you get, e to the third, and then f prime of 2 again. All right, so if you look at that, you have -4e cubed, and then you have 2 times 1/2 is 1, 2 times 1/2 is 1, so you have -4 cubed, -4e cubed plus e cubed is -3e cubed. Yikes. Now we're just going to put it into the Taylor formula. So make sure you get the center correct. That's like the one thing that could really go wrong at this point. So e cubed is the value of the function plus first derivative is e cubed, x minus 1 to the first over 1 factorial plus second derivative is -3e cubed, x minus 1 squared over 2 factorial. There you go. All right, that was a good problem. Let's take a look at the next one. So the summation above can be rewritten as a familiar function written piecewise with 2 branches, one for x not 0, one for x equals 0, write that function. Okay, so when I'm told it's a familiar function, I think like the factorial is going to tell me what's going on. So I see 2n plus 1 factorial, I immediately think this is sine. To make it sine, I got to make it fit. So I need like u to the 2n plus 1 over 2n plus 1 factorial. That's what I need to make happen. So I'm going to take my original thing here. I have 3 to the 2n and x to the 2n. So I'm going to make that 3x to the 2n. We're trying to build it. We're trying to make it look like we want it to. And we still just have this 2n plus 1 factorial. We really want 3x to the 2n plus 1. So what I'm going to do is I'm going to employ a little trick. I'm going to say, if I multiply the top by 3x, I would accomplish that goal. But I can't just do that because it changes the function overall, right? So instead, I just multiply by a weird form of 1, which is 3x over 3x. Very common thing to do. So in doing that, I'm going to use the 1 in the numerator to make 3x to the 2n plus 1. I'm just going to factor out the 1 over 3x that we still have there. So we have this. And then at this point, we have our -1 to the n. We have 3x now to the 2n plus 1. So things are looking good. And then 2n plus 1 factorial. Okay, so if we ignore the fact that n equals 1 is where we're starting, this would now be sine, right? But we can't ignore that, right? We're starting at n equals 1 instead of starting at n equals 0. So what must have happened is the term that you get from n equals 0, we just subtract it off, right? So I need to figure out what happens at n equals 0. If I take 0 and plug it in for n, I get -1 to the 0 is 1, 3x to the first, and then 1 factorial. So I just get -3x. Or rather, I get 3x, but I'm going to subtract it off. So we're going to have -3x here. And that is because when n equals 0, that's what you get, 3x. You have to subtract it off. All of this over 3x. Now, there's a thing that happened. We introduced the idea of dividing by 3x. As soon as we introduced that, we said x can't be 0 because you can't divide by 0. So this is where we're going to get 2 branches. The other thing we need to do is think, well, what if x is 0? So if x is 0, look at the original summation. It just becomes the sum from 1 to infinity of, if x is 0, you get 0 times all that stuff. You just get 0. You're just adding up 0, which means at 0, you're 0. So our function, rewritten as a piecewise, is sine of 3x minus 3x over 3x when x is not 0, and then it's 0 when x is 0. I'm going to put in a screenshot here of the graph of this thing and, I don't know, maybe like 20 or so terms of the summation, so you can just see they're definitely the same on their interval of convergence, which is kind of an amazing thing you can do with series. All right, let's take a look at one more problem. We want to evaluate the limit as h approaches 0. As soon as I see that, I'm thinking limit definition of the derivative. That's like a key thing that your brain should look at. 1 over h times the natural log of 1 plus h over x. So as I said, limit definition of the derivative. So now we just got to work it out. So like why? Why is this that? This is actually a pretty, I want to say common, but I can't tell you how many times it's shown up. I don't know. This has been on the AP exam more than once. So what we're going to do, it's a little manipulation. It hasn't been on recently. They're not as in love with these properties anymore. I'm going to get a common denominator inside the parentheses. So I have x plus h over x. Now what I'm going to do is I'm going to use a property that division within the log becomes subtraction between logs. So we're going to have the limit as h approaches 0. We'll have the natural log of x plus h minus the natural log of x, and then over h. This is the limit definition, right? So it's f of x plus h minus f of x over h, which means f of x is natural log of x. We're finding the derivative of natural log of x. That's all we're doing in this problem. And then that answer is going to be 1 over x. Kind of debated. I mean, x can't be 0, definitely, in this problem. I would say that x is probably supposed to be greater than 0. I'm not really going to worry about it in this case. I don't think it's really the point of the problem. But that's kind of a clever little problem we can do. All right, that's the end of this problem set. I hope this was helpful, and good luck.